Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome everybody here and in virtual reality. I'm really pleased to have Roman Minevich return to Microsoft Research. He is completing his PhD from Tel Aviv University under the direction of Professor Muli Segiv. Roman is known for doing a lot of interesting work around the area of shape analysis, in particular how to make it more efficient and precise. And today he's going to tell us how that applies to both sequential and concurrent programs. Roman, take it away.
Okay, thank you, Tom. Is it on, by the way? Can you hear me?
Yeah.
Okay. So I'm glad to be here. And let me start with this by showing you this program. So this program, along with some properties, poses an interesting verification problem. So what this program does, it's an implementation of a concurrent stack in terms of a single linked list. And you can see that it has a push operation and a pop operation. And so now I want to answer some verification. I want to verify some properties. For example, so you can see that it has pointer updates. And for example, I would like to verify that every pointer update is safe, that I'm only going to access legal memory, that I'm not going to cause any memory leaks, and that I'm not going to, so that the list is going to remain acyclic, which is what is meant by this program. And another property that I'd like to verify is that this stack is linearizable. So I will just, so I'll come back to this, I'll define linearizability a bit more precisely later, but right now let me tell you that linearizability is the major criterion for concurrent data structure. And intuitively it means that every concurrent execution of the data structure has a corresponding sequential execution. So in some sense, the operations, the push and pop operations, you can think about them as atomic operations. And you can see that this problem is actually very challenging. It's challenging because of different things. For example, so we have dynamic memory allocation, which means that the number of objects is unbounded. Of course, we have the list, which is a recursive data structure, so we have to reason about it. As I said, we have destructive pointer updates. I don't have any assumption on the number of threads, so the push and pop can be executed by any number of threads. And also, so this implementation is non-blocking. It uses compare and swap for synchronizing the threads, and which means that several different threads may be accessing the same object simultaneously. So another thing that makes it challenging. And the good news is that what I'm going to tell you about are some ideas and techniques that would let me, for example, verify the linearizability and the other properties that I've talked about automatically for an unbound number of threads. Okay, so for now, when I talk about concrete states, I'm going to, in my analysis, concrete states are simply labeled graphs. And these graphs represent both the dynamically allocated objects, such as the list elements, and also you can see the hexagons actually represent thread objects, and I have the program counter written inside. And I have edges to represent list fields, and also edges to represent thread local variables. So you can just think about, so I'm going to present different kinds of shape abstractions, and these abstractions are going to work uniformly. So they're going to handle shapes, these labeled graphs, and they're going to handle uniformly objects and control. Okay, so yeah.
Actually, if you can go back one slide, I'm sorry,
Sure.
Interject, but what I want to say is that, well, so I program in C# these days, or Java, or whatever, and I don't really write code like this at all. Why should I wait?
Well, maybe you don't write code like this, but I mean, okay, so this is this implementation in C++, but there are also implementations of these concurrent data structures for Java, and I haven't talked about C#. I guess there are also implementation.
Sure, but,
So the idea is
using them, so you'd like to know that they're correct. Let's move
right.
on.
Okay. But the idea is to have efficient implementations of highly concurrent data structure. And so really there are two kinds of classes of abstractions that you can think of. And you can think about abstractions as in terms of the invariants they represent or the forms of the invariants. So we can have so the disjunctive school says that you should represent invariants in terms of disjunctions. And so join operation that merges different abstract states is simply disjunction. And this approach is very popular in the model checking community. On the other hand, there's what I call the partially disjunctive school, in which invariants are represented by conjunctions or universal quantification, which is just the infinitary version of conjunction. And so in this kind of invariants, when you merge different abstract states, you actually lose information by the join. I'll show you an example. And so this approach is very popular in the abstract interpretation community and also in the data flow community. So here's a research problem that interests me. There are various kinds of shape abstractions, and they usually use so these very highly precise, high precision shape abstractions actually use join as actually disjunction as their join operation, which means that they are very precise, but in some sense they're more precise than they need to be, meaning that they actually track more correlations that they need in order to prove the properties that we are interested in. And because they use disjunction, that means that the state space very easily blows up. So these abstractions can be either exponential or they're even doubly exponential abstractions. And so my take on this is that I'm going to define a different class of shape abstractions that are partially disjunctive, and I'm going to design them in such a way that they are going to be precise enough for the class of programs and properties that I'm interested in proving. And I'm going to also aim them specifically at reducing different kinds of exponential factors, and you'll see some examples later. And the benefit that I get is orders of magnitude of speed up. So really the challenge is, how do you design these partially disjunctive abstractions for the heap? And so this is very challenging because the objects and the threads are anonymous. You can't actually reason about the correlations between the addresses. The addresses are completely coincidental. So here are some results that I have in my thesis. The first one is a framework to create these partially disjunctive abstractions. And they're defined in terms of the concept of heap decomposition, which I'll talk about, which is the main issue in my talk. And the idea is that instead of tracking correlations for the global heap, what you do is you take a heap and you break it apart, you decompose it into a set of smaller subheaps. You track the correlations inside the abstract properties inside each of these subheaps, but you abstract away the correlations between the different subheaps. And this is good because suppose you take different full heaps and you decompose them. So some of the subheaps may actually appear in the different full heaps, which means that after you create this abstraction, you're actually reusing them, and that helps you reduce the size of the state space. And I've created an automatic system that lets the user specify different kinds of decompositions. So the user can specify decompositions, and it automatically generates an abstract interpreter, which is a static analysis, which is guaranteed to be, it's always guaranteed to be sound, and the abstract transformers are feasible. And I've applied this technique both to sequential programs that analyze multiple data structures, and also to concurrent fine-grained programs for proving linearizability for an unbound number of threads. Okay, so in the rest of the talk, so first I will start talking about, I'll show you some examples of disjunctive and partially disjunctive abstractions. And then I will go on to introduce the concept of heap decomposition. So I'll show you some examples and I'll define it more precisely. And then I'll show you the application to creating kind of a thread-modular analysis for fine-grained concurrent programs. Okay, so let's start with some background. So in static analysis, what we usually do is we take an infinite state space and we create a finite abstraction. So think about this yellow square as representing the infinite number of points inside it. And let's pick some points, these green points that I've marked. And the way to create an abstraction is by creating a finite. We partition the state space into a finite number of equivalence classes represented by these squares. And the way the abstraction works is by mapping every one of these green points to the square that covers it. And that gives you the abstract state space, which is just the set of these squares, so it's finite. And on the left side, you can see the logical representation of this abstract state, which is, as you see, it's a disjunction. So this is an example of a disjunctive abstraction. So it's just a disjunction of these inequations that correlate x and y. So now I told you that when you have two abstract states and you merge them together by join, so this is something that happens on control flow paths, when control flow paths in the program actually join. So when you put them together, what you do is you don't actually lose any information because you simply use disjunction. So you just keep the set of disjunction that you used to have. So this is very simple. Now, here's an example of a partial disjunctive abstraction. In this abstraction, what we do is we take a set of points and we cover it by a single rectangle. And so you can see that the abstract states are actually conjunctions that correlate x and y. But in this abstraction, actually, I'm tracking x and y independently. So when I take two abstract states and I join them, what do I get? I get a single rectangle that covers all of them. And what you can see is that finally I get a single conjunction. So I've lost some correlations between x and y. And you can see the loss of correlation by these red corners, which represent the loss of precision that I get by the join operation itself. So here join is obviously coarser than disjunction. So let me now compare disjunctive abstractions to partial disjunctive abstractions in a more general way. So in disjunctive abstractions, we don't lose any information when we join abstract states that come from different control flow paths, as you've seen in the example. The downside is that because we were using disjunctions, we immediately get exponential blowups because we can get all the supersets of the states. And now there is an important question with abstractions is, given a program and a property, can you actually automatically come up with a good abstraction for this verification problem? And this problem has been studied. There's a large body of work, for example, for predicate abstraction, which is a disjunctive abstraction. So all this work about counterexample guided abstraction refinement that gives you some very good answers by using parsimonious abstractions, for example. And so for partial disjunctive abstractions, we actually lose many correlations when we merge abstract states. The benefit that we get is that we can actually reduce many exponential factors. And now for the question is, how do you come up with the right abstraction? So that question has not been studied as much as in the disjunctive case. And it's a bit harder because in some sense you have to, so in the disjunctive case, when you run these counterexample guided refinements, they usually consider just one trace in the program and they try to rule it out by coming up with a more precise abstraction. For partial disjunctive abstractions, you actually have to learn or generalize from multiple traces simultaneously. So it's a bit harder. So now let's go and so now I'm going to talk about how do you come up with these partial disjunctive abstractions for the heap. So for the heap, scaling is a major issue. So the kind of abstractions that we use are very costly. They can be doubly exponential. And of course, the state space is infinite because we don't have any bound on the number of objects and the number of threads. So, and concurrency complicates things. You can have different kinds of connections between the threads and the objects. And so now the question is, how do you create these partial disjunctive or Cartesian abstractions for the heap that keep the right correlations but lose the... So as I've shown you in the example with the numbers, it tracks some correlations between the numerical values and we lose others. So we can't, because the semantics we use for the heap is tallest, we can't actually use the addresses. So we have to do something else. So that's a challenge. And as I told you, there's no bound on the number of objects and threads. And the question is, which kind of correlations are actually important for different kinds of programs and properties. So here's CEGAR-like techniques can actually help us, but I'm not going to really address this in this talk. What I'm going to show you is a class of programs and properties, and I'm going to show you how to come up with the right abstractions, with the right partially disjunctive abstractions for this. And another note that I want to make is that it's possible that your abstraction actually, it's not always the case that if your abstraction is coarser, then it's more efficient. I actually show you one example where you actually keep less correlations, and then the analysis becomes actually less efficient. So now what is the idea of, so now I'm going to tell you about partial disjunctive abstraction using the idea of heap decomposition. So what is this idea? So you take a heap and you decompose it into a set of subheaps. So what is it actually, I'm blocking your view. So what does this set of subheaps actually represent? So it simply represents the full heap that we started with. So we haven't lost any information yet. Now let's take another full heap and decompose it. We get these 4 subheaps. And then what do they represent? Exactly the heap that we started with. So again, there's no loss of information. But now what happens if we take both of them and we decompose them together? Now we get a set of 7 heaps. And they actually represent the same. So they represent both of the full heaps that we saw earlier. Of course, it's a sound abstraction. But in addition, they also represent these 2 full heaps, which you get by mixing different subheaps that we've seen earlier. So for example, how do we get this full heap? We take x and y, this subheap from here, and z from here, and we take p and q from the subheaps over here. We compose them together, we get this full subheap. We get this full heap by taking this subheap, that subheap, and the subheap from here. So you can see that you can mix these subheaps, you can compose them together and create, and they represent actually new full heaps that weren't there in the beginning. But not all the combinations actually are consistent. For example, if you take x and y from here and y and z from here and you compose them together, then this is actually not consistent. So I haven't defined the right exactly what is the decomposition that I'm talking about, but you see examples showing that not all the compositions are actually consistent. So now I'm going to talk about an instance of this general heap decomposition idea, which is decomposition into connected components. And now I'll actually contrast 3 kinds of abstractions. One is a disjunctive abstraction. So here's an example of a program. So let me start with this simple memory configuration, which has 3 objects pointed to by x, y, and z. And what this program does is non-deterministically inserts a link between x and y or y and z. So we get these 2 abstract states. When we merge them together, we simply get their disjunction. And now we can actually, and suppose we want to assert that you cannot get from x to z in 2 steps. So we will simply check it on each of these full heaps, and the property holds, so that's good. The downside is you can see that the state space is going to grow. And usually, so this is the cause of exponential blowups that we get from disjunctions. Here's a kind of abstraction which is a partial disjunctive heap abstraction. It starts the same, but now when we merge these 2 states, we start losing correlations between the edges. So we remember that we have 3 objects, but we lost the correlations between the links. So these are May edges. So we're not actually sure whether it's possible or not possible to get from x to z in 2 steps. And so we're not able to actually to prove this property. So we can think about the space of all possible heap abstractions. So now I've shown you a simple example of a disjunctive heap abstraction. And I've shown you an example of an independent attribute heap abstraction. And now I'm going to talk about connected component decomposition. I'm going to define it and apply it to this program and show that it's actually more precise. And in using it, we can verify this property for this program. So the idea, as I told you, is to take a heap and now decompose it into a special way. So the way we decompose it into the set of disjoint memory regions. So in this case, there are these 3 objects. Each of these objects is actually its own memory regions. There are no links between them. So we split it and we get 3 subheaps. What do we actually maintain in this abstraction? We maintain all the aliency relations and all the reachability relations. What do we lose? We lose actually the correlations between the different data structures. So, so what does each of these subheaps actually represent? So the abstraction works by projecting the heap on just a portion of the heap. So when we think about these subheaps, what they actually represent is all the heaps that have so there's this rest of the heap that we don't know anything about, except that there are no edges going from here to there, and y and z can only point to some other part of the heap. And we can represent the same idea in logical notation. So this, for example, says there is a connect component that contains x, but it does not contain y or z, and there are no edges. So you can see that there's no self-loop, for example, from x to x. And similarly for these two. So here's a set of subheaps that I got, the decomposed subheaps. What do they actually represent? So you can see that this subheap, for example, represents a connected component that contains x, y. It does not contain z. And the set of edges that it has is just a single edge from x to y. And this one it's a connected component that does not have x or y. It has z, and there are no edges. And similarly for the other two. And what does this set of subheaps represent? So remember that the meaning of a set of subheaps is given by composition.
Quick question. Do you need this closed assumption that you know what all the x, y, and z's are, or is this sort of open for any other object that I might know about that's different from x? So before you always sort of make it explicit, it's not z. Is that just for your slides, or is that a fundamental thing you need to know in the universe?
So in this specific, do you mean that whether I know that the set of variables is whether I know the set of variables in advance or not?
Yes.
So for the kind of analysis I've used, I do know the set of variables, but I have to think what it means for. I think the same idea. I could actually use it for a library where it actually don't have any assumption on the entire set of variables. But I have to think about it a bit more. But in the setting that I applied, actually I've used it for programs where the set of variables is known in advance. And so the meaning of a set of subheaps is given by composition. So a set of subheaps represents all the full heaps that I can get from composing these subheaps. For example, I can take the two on the left and compose them together, and they represent this full heap. I can take the two on the right, compose them together. I get this full heap. And when I compose, I have to take care that all the variables appear there. So for example, if I try to compose these two, you can see that I have x and z is the logical notation, but y doesn't appear there. So this heap is not represented. It's not a full heap because it doesn't contain all the program variables. And also, I cannot. If I try to compose different subheaps that have variables in common, then I get actually inconsistent heaps. For example, if I take these two and I try to compose them together, they're actually inconsistent because of the decomposition that I'm using. So if we look at the logical notation, we can see it. Suppose we try, so when I compose, I actually take the conjunction of these two. So suppose I try to take the conjunction of them. So this is the invariant that I get, and let's see what it says. It says that the heap contains a connect component. It contains x and y, and definitely not z. And simultaneously, it contains a connect component that does not contain x, but contains y and z, which is impossible. So this is not represented. And this is actually going to be important. So let's go back to the example that we saw. Let us apply this decomposition. So we started with this memory configuration. We split it apart. Now we go to the left and go to the right. We get these subheaps. We join them together. We get this set of 4 subheaps that I've just shown you. And what do they represent? Exactly these 2 full heaps. And you can see that for each one of them, the property holds. So I'm actually able to verify this property for this program.
Can you go back and just do that one more time a little more slowly?
Sure. So I start with this memory configuration. So the full memory configuration used to have these 3 objects simultaneously. I split it apart. I applied the decomposition. So when I go to the left, this is something that I actually went over quickly. What I do is I temporarily compose some of the subheaps.
Mm-hmm.
So when I try to install a link between x and y, I join these 2 subheaps. And then I try to decompose, and I get these two subheaps, and I do the same thing for the right.
So there is always, so you always sort of recompose after.
Right. So during the transformer, I temporarily compose some of the subheaps. I try not to compose. If I try to compose all of them to get the set of full heaps, of course, I get all the exponential blowups that I try to avoid.
So you're going. This is something like a focus operation.
Right. It's a partial concretization. So I temporarily refine my abstraction.
Right.
So in this case, for example, for this transformer, I temporarily refine my abstraction by saying that I'm going to decompose the heap, except if it contains x and y simultaneously. For the subheap that contains x and y, I'm not going to decompose it. So what happens is that I'm going to get a subheap which looks exactly like this, except that x and y are in the same subheap. And then I'm going to apply this transformer. I'm going to install the link. I'm going to get this, and then I'm going to decompose. And because I install the link, this becomes a single component, and the same for the right side. And then I just put them together. And as I said, this is their meaning, and I'm able to, yeah.
So you might be going to talk about this, but how do you verify the property of the full heaps without actually enumerating the full heaps?
Right. So what I'm going to do, I'm going to apply just a small number of subheaps that are going to. So, for example, suppose I have this set of four subheaps, and I want to verify that you cannot get from x to z. So how would I do it? I would start from the subheaps that contain x, so these two, and then I'm going to look for the rest of the heap. So actually, in this case, I don't really have to do it. So because suppose I start with this subheap, and I ask, can it possibly be a part of a full heap which contains a path from x to z? That's not possible because this is a single connect component. Remember that what a connect component represents is a heap that contains this part, and there are no edges between this part and the rest of the heap. So I know that it's impossible to get from x to z from here. And I can actually apply this very local reasoning for each of these subheaps. But sometimes I have to do some composition. So suppose I actually I don't use this reasoning on the connect component. So what I might try to do is actually try to take this one and look for z and compose them together to get a slightly larger subheap. So the idea is to get the smallest subheaps, to compose the smallest subheaps that would allow me to verify the property.
So suppose on the heap on the right, if you had x points to y, y points to z, and on the left you had x points to y and z, and then z. If you merge these two, what will be the result?
Again, you're changing the.
So let's say on the right side you actually have an extra edge from x to y.
Okay.
And then if you want to merge, you will still have two connected components, one which contains just x and y, another one which contains both x, y, and z.
Right, I'll have this component, and this will be a single component that has x, y, and z simultaneously in the same component.
And so your formula can get as large as the number of ways you can partition your universe.
Right.
That can be very large.
Right.
Exponential or factor, I don't know.
No, I mean it can. No, it's linear in the number of program variables. So a connect component contains a subset of the variables. So it can at most have all the program variables. So suppose the number of variables is n. So
each component can be linear in the size of a variable, but it can have different components.
No, but if you're not allowing garbage, then every connected component starts with some program variables, right?
There's an exponential number of subsets.
the number of subheaps is indeed exponential. You're right. So I mean the size of the state space. In the worst case, I haven't actually reduced the height of the lattice. So it's still it's a smaller exponential, but it's still exponential. You're right. It doesn't magically become polynomial with this decomposition. It's not. No. Yeah, but actually, okay. So I haven't shown a particular kind of abstraction. So actually, for the particular kind of abstraction that I'm going to apply connect component decomposition, the abstraction that I start with is also exponential. After I decompose, I still have an exponential factor, but empirically it's better. I'm going to lose some correlations. So for the more general kind of decomposition, you can actually tune them to have a polynomial state space in the worst case. But here I haven't done it. So for example, I can try to further decompose the heap and try, so for example, I could take this subheap and try to lose the correlation between y and z. But this, or I might even have an object that's pointed to by several variables, and I can actually try decomposing it by losing the correlations between, losing the aliasing relations. But that usually is, in practice, that turns out to be a bad idea. So I'm not going to do it. So you can think about more finite decomposition. That I'm actually going to discuss finite decompositions, but in this scheme I'm not going to use it. So this is as fine as I get. A single connected component is the smallest subheap that I get. Okay, so we've had this. And now you might ask me, how do you actually get a finite abstraction? So using decomposition alone, you don't get a finite abstraction. So I'm going to actually combine the idea of heap decomposition and other kind of bounding finitary heap abstractions. So there are different kinds. So there's a canonical heap abstraction, and there's a kind of abstraction that I devised for a possibly cyclic list. And so let me show you just one kind of. Let me show you this abstraction. It's pretty simple. So suppose you have a heap that has several program variables. So the idea of this abstraction is that I'm going to maintain important objects, these blue objects that are either pointed to by program variables or have more than one incoming edge. And what the abstraction does, it maintains them, but it's going to abstract the length of these of the sublists that connect them. So I get this this bounded heap. So this heap may be unbounded, and this heap remembers that the length of the list is either 1 or greater than 1. So it becomes bounded. So in the rest of the talk, I'm not going to really make a distinction between the concrete heaps and these bounded heaps. So just think about them as different kinds of labeled graphs. So the idea of decomposition works well for both concrete heaps, for these concrete labeled graphs, and also for these bounded labeled graphs. So it's not a distinction that that is going to be important for. So the idea of decomposition is orthogonal to this bounding abstraction. Now, really, to get a finitary abstraction, what I do, so I can compose these abstractions in different ways. For example, I can start with full heaps and then decompose them. So now I get a set of these, a set of subheaps that are not actually bounded, and then apply this bounding abstraction to them. So this might be a very, very long list, and then after I bound it, I get this bounded subheap. And the meaning is given by first exploding these heaps, and then composing into the set of full heaps. Or I can go the other way around. I can take a heap and then bound it, and then decompose this abstract heap.
So does that mean you can't deal with linked data structures in which the number of nodes with multiple incoming edges is unbounded?
Not in this abstraction. So this abstraction is specifically aimed for a single linked list, but there are actually extensions of this work that using very, very similar ideas of keeping important objects and then abstracting away some paths between them. That so people actually use these ideas and extend them to trees and other kind of data structures. But I'm going to use this abstraction. Well, first I mentioned because I invented it, which is one of my results, but also because I'm going to use it in my slides. So for right now, let's just think about single linked list. And so actually, in the kind of decompositions that I'm using, these operations commute. So it really doesn't actually. It's really not important. So in practice, the order actually doesn't matter. I get the same result. So let's see that this example. So I showed you a toy example. But let's see a more real example that shows actually what kind of exponential factors do I aim to reduce. So in this example, I have a precondition. You don't actually have to read it. You don't have to read the precondition. What it says is that we have this one element list that are pointed to by h1, t1, h2, and t2, respectively. And what I want to prove is that for every iteration of the loop, the invariant looks like this. I have these two lists that are disjoint. They're acyclic. h1 points to the first element, t1 to the last one, and same for the second list. So it's a very simple program. What does it do? It creates some object. It puts it in a list element, and then it non-deterministically inserts this element into the first list or the second list. So if I want to verify that this loop invariant holds, the observation is actually that I don't have to track the correlations between the properties of the different lists. I can actually track them separately using connected component decomposition. And so this is what I'm going to do. And so this is actually a very common pattern in device drivers, where you, so this might be an IRP object which you insert into a list. Sorry, is there a question? Suppose I run a disjunctive heap abstraction. So what do I get at the loop head? What I get is 9. Yeah? You seem to be confused.
You're going to find a bug in the program? Or?
No, there is no bug.
There's no bug.
This program doesn't have a bug. I want to verify that it's actually...
Okay.
I want to verify that this property holds, and indeed it holds. I don't have an example with a bug, but
Trivial holds.
it trivially holds? In what sense? I mean, you have to reason about recursive data structures. What does trivially hold? I mean, I don't see how you can actually verify this locally. I mean, when you actually try to dereference, you have to track the aliasing relationships. You have to know which regions exist on the heap. You have to know that these subregions are actually disjoint. So if for example, if you use a flow-sensitive pointer analysis, you can't actually. All this is going to be clumped together into one single points to node. And so if you run a disjunctive abstraction, what you get are these the disjunction of these 9 abstract states. Each of these states is made of a conjunction of the properties of each of the lists. So for example, for the first list, it can either be of size 1, 2, or more than 2. And same for the second list, 1, 2, or more than 2. And then you get all the combinations of these properties, so you get 9 abstract states. So actually what we'll see here is that you can see that in each one of the rows, the sub-heaps for the second list are actually, they keep reappearing. So these are common subgraphs. And same for the rows and the list number 1. You can see that in the rows, these subgraphs for list number 1 are also common. So I actually want to exploit this. So now suppose I apply connect component decomposition to these heaps. So what do I get? I get just these 6 heaps. In this case, I don't actually lose any information because, so what do they represent? So if you take any one of these 3 subheaps and you compose it with any one of these 3 subheaps, you get exactly one of these 9 states, 9 abstract states that I'm showing here. But you can see that I went down from 9 to 6 states, which is nice. And this is still, if I use this kind of abstraction for this program, it's still precise enough to prove the property that I wanted to. But I actually lost the correlations between the 2 lists. So now you can think about a generalization of this program that has any number of lists, some k lists, for example. And if I use this kind of abstraction, so if I compare to disjunctive heap abstraction, I go down from 3 to the k to 3 times k abstract states. So this shows the exponential reduction in the state space that I want to have. Okay?
Going back to Nikolai's point.
No, I understand it. T is the tail of the list.
T.
And you're just appending to the tail.
Let's see. So.
That's just not.
I guess. No, but I guess the main
T1,
point is
T2
really
are
not
the
so
tail.
much about. I mean, there's a difficulty in updating, maintaining the predicates reach in disjoint lists under these assignments,
Right.
destructive updates.
Right.
And fundamentally, that's a difficult problem. But what you're addressing is really efficiency.
Right.
Maintaining efficiency and precision. So there's the problem of precise update, and then there's the problem of sort of efficiency. So really here, what you're showing is that we could do it sort of the normal way.
Yeah.
With maybe just some verification condition generation, some checking in a theorem prover suitably enriched with these predicates. But we might have to explore unnecessary correlations. Here you're
Right.
showing a decomposition that retains the efficiency. Is it?
Yeah, exactly.
So really, I mean, your technique is orthogonal to the question of the precise
Right.
update.
Right.
In some sense, anyway.
Yeah.
Is it obvious that the partial disjunction is always smaller than the full disjunction, or you can think of corner cases where the partial thing will be even larger?
Yeah, it can be larger. I mean, if you actually suppose you take this heap and you decompose it, you get 2 subheaps. So, I mean, if you compare the number of heaps and subheaps, then yeah, it can be larger. It can even be worse in practice. You might actually lose important information and start exploring all sorts of impossible situations. That could happen. But right, so for the class of programs that I'm interested in, for example, these divide traversals, what they do, they have a bunch of lists and they manipulate them. But really, if you want to prove cleanest properties, that you don't actually destroy these lists and don't do null pointer updates, memory leaks, then actually you don't really have to track the correlations between the lists. So that's the observation that I used. Okay.
When you say correlations between lists, you mean like the actual values in the list? Because I mean, if
No, the correlations between.
Then you would actually keep them because you're not going to divide them, right? If they're pointer correlations, then your subdivision will say, well, they're connected, then so you won't be able to lose that information, right? So what correlations are you talking about?
Right, so these are the correlations between the abstract properties. So for example, so here the correlation that I have is that simultaneously the first list has a length greater than 1, and the second list has length exactly 1.
So for example, counting properties or
Exactly.
size properties.
Right, exactly.
I think you're using the fact that the heap many times is composed of different independent things, and then there's no reason to always talk about all of them,
Right.
all of them together, right? And
Yes.
that's in practice that happens a lot.
Yeah, in practice. So this is what interests me. So okay, so
But a purely disjunctive approach for that, which would not eagerly expand and canicalize the data structure, could also take advantage in this case, right? You're going to talk about that later, or
I don't really understand. Eagerly is
so
going to.
I'm not sure exactly if you have such a basically local properties, and these subheaps are kind of independent.
They're
You
not.
could
They're
also
not.
capture.
Okay, so, sorry. So they're not statically independent. It's not like you can look at the program and say. So for example, so maybe this is a trivial example, but temp is going to be used both in both of these lists. So it's not like you can run a points to analysis and say, okay, these are going to be forever disjoint, and so let us just track them. Let's just separate the problem into a set of sub-problems. So sometimes, so this example is just a temporary variable, but there are actually examples where some of the pointers are actually going to be used in one list, and then they're going to be used for the other list. So you can't actually statically determine the right kind of decomposition. So the decomposition that I'm using is determined dynamically during the analysis as the connected components get connected and then disconnected. So it's dynamically determined decomposition. Okay. Yeah.
So I have an orthogonal question. So in programs, you have lots of fields, right? You have the next field, you have the pre-field, and so when you're doing this analysis, you can really focus at one field at a time.
So this is not. So in this example, this specific example, for the list examples that I have here, they have just one field. So but this is an interesting idea. So this is not the idea that I explore here, but it's so what you're suggesting is a different kind of decomposition, which sounds interesting.
So for example, if you just focus on one field, like the set of connected components you get would be different from if you just focus on another field.
Right.
Right. And so usually these linked lists, they might not be reachable through the next field, but they might be connected in other ways. Usually they're part of some bigger data structure.
Right. So you can consider different kinds of generalizations of these reachability properties that you use to determine the decomposition. So maybe you can take the union of all fields and then create your connected components. But this is one. But right now, what I want to show is just one specific instance that shows how this idea of decomposition is interesting and why it's worth considering. And later I'm going to tell you about more general kinds of decompositions. But here I'm just exploring one particular decomposition. And now there's also the question of, so in abstract interpretation we have the question of how do you, which kind of abstractions do you use? And also the question of how do you approximate the concrete semantics of the program under your abstraction? So, and this, and we call it how do you actually compute abstract transformers? I mean, transformers that over-approximate program statements under the abstraction. And so for this specific decomposition, I considered this problem theoretically, and I found out that it's actually NP-complete. So you can't actually, so unless P is equal to NP, you can't actually avoid doing something which is sub-exponential, which is better than maybe just composing all of the heaps. And so what I did is I compromised. I devise a set of sound transformers that are polynomial. Intuitively, they only compose as much of the small number of subheaps, no more than 2 and 3, as much as we need to compute to over-approximate the program statements. And I found out that these are actually very useful for the kind of analysis that I have. And the overall analysis, when I applied it, it was precise enough for a class of programs. I'm going to show you some experimental results. And I got very nice speedups. Okay. So here are some experimental results. So I applied this analysis to both artificial examples and also Windows device drivers. So this is for the serial device driver, and so this is for kind of a slice of the serial device driver. This is the firewire driver, and these are programs that take a list and split it into 5 lists, or take 5 lists and join them together. And you can see, so this goes to your question that you can't actually statically determine the decomposition, because they actually depend. At some point, I mean, all the lists actually interact with all of the other lists. At some point, they're actually all in the same component. And so this is actually an artificial example that I created to show that you can actually lose important correlations. So in this program, this program maintains a queue by 2 stacks, 2 single linked lists. Yes.
What was the property that you were checking in the Windows device driver?
So I was checking basic cleanness properties, that you don't have memory leaks, null pointer updates, some properties about disjointness of different lists, reachability between program variables. So I have a prototype that lets you write assertions in terms of reachability, cyclicity, acyclicity.
And you also need to provide loop invariants again.
No. It automatically infers loop invariants as is standard in abstract interpretation. So it just runs the abstraction, it explores the abstract state space, and automatically proves it. So there are no annotations. I mean, you can write your assertions, but it's only for checking. And so the queue, so this is the queue that's maintained by 2 lists. And so the thing here is that in order to know that the queue is empty, you have to simultaneously know that the 2 lists are empty. And if you actually lose the correlation between them, you can't tell that. And that's why in this example, I actually lose important information. I can't actually prove important properties. And if I compare the number of shape graphs that we get from the disjunctive abstraction to the number of subgraphs that I get from the component decomposition abstraction, then you can see that usually I have nice reduction. So I was actually able to reduce the size of the reachable state space by usually by order of magnitude. But in this case, actually, the state space is larger because I'm exploring impossible situations. And in terms of the speedups, I also have very nice speedups. But for this example, again, it runs twice as slow. So this goes back to what I told you in the beginning, that sometimes losing correlation doesn't mean that you get more efficient analysis. So it's actually important to tune your abstraction such that it doesn't lose too many correlations. So now the question is, yeah.
So were there multiple procedures in these examples, or was it a single procedure? Like, was it inter-procedural analysis, or?
So these examples are interprocedural, but they don't have recursive calls. So I just use the call string approach.
So you just inline all the calls, right?
Yeah, I'm using yeah. So the abstract state space has these lists. It also maintains the call stack, which is finite, so yeah, it's inlining. So another question is this the end of the road? I mean, we have this decomposition, we have these nice results, but as some of you mentioned, sometimes you can get the heap can get very complex. You can have things that are not lists, and very often the heap is actually it can even be just a single connected component. So that means that you can't actually. So this decomposition actually doesn't buy you anything. And another question is what happens when you have concurrency? How do you actually define the compositions that allow you to reduce, for example, the interleavings, the exponential blowups due to the interleavings? And sometimes you might it's actually important to keep correlations across different connected components. So one trivial example was this queue examples, but there are other examples. So, okay, so this leads me to the idea of more generalized kind of decompositions. So for this purpose, I came up with this system. So it's a parametric system for heap decomposition, which you can experiment with different kinds of decompositions. So what you do in the system, you specify a decomposition parameter, and you have a specification for the abstract transformers. And and the subheaps that you get, they don't have to be, they can actually overlap. There's no need for them to be disjoint. And they also apply for concurrent states. And soundness is automatically guaranteed. So you can think about any kind of wild decomposition that you want, and any specification of the transformers, and you can never lose soundness. You can only lose precision or efficiency. So let me show just the kind of specification that I'm using. So this is for. So actually, I'm cheating a little bit. I'm showing the one kind of specification that we're using. So in this kind of specification, what you do is you define a finite set of unary predicates that capture a subset of the objects. So suppose you have this full heap, this green circle, and so P1 holds for a subset of the object. So V ranges over the objects and threads in the heap, and P1 holds for a subset, and P2 holds for another subset. They may overlap. And what the decomposition does, intuitively what it does is that it actually projects on that portion of the subheaps. So I'm maintaining the set of objects here and all the connections between them. But I'm losing the connections between different subheaps. So this is just to show that it's, so this is the parameters that I'm using. And going back to the space of abstraction, so it's a more general kind of abstraction. It's parametric, so you can define different kinds of, so you can actually use it to describe different kinds of abstractions. And I've applied this abstraction to prove linearizability.
So how is it different from the symbolic heaps that Podolsky and Thomas uses, like this parametric unary predicates?
So the unary predicates. There are two classes of unary predicates. The unary predicates that they use it for the bounding abstraction. Here I'm using it for the composition. So actually, the truth is that I integrated this idea into the TVLA system, where I have actually two classes of predicates. One class of predicates is used for to bound the heaps, and the other kind is used to decompose. But you can actually, at least theoretically, you can try to adapt this idea to different kinds of abstractions that not necessarily built in terms of predicates.
Are you going to talk about how you compose again these new decompositions? Before, when we had the decomposition based on reachability or connectivities, right? It was sort of obvious how you would compose again and which compositions were not valid, right? But now in this more general form, that seems much more difficult, right?
Right.
Are you going to talk about that?
Not so much. Okay, I'll go back to this point in previous slides, and I'll try to supply some answers. Just a quick answer. What I'm actually using, I'm using a meat algorithm for three-value structures, so which enables me to actually take two subheaps that may overlap and create a set of refined heaps that actually contain both of them. So what I'm actually using properties of the different abstract nodes, of the summary nodes, and I'm actually trying to see which ones can actually go together.
I see. So you detect during the analysis whether you have an inconsistency
Right.
with the state decomposition. You know which ones you don't even have to try to compose.
Right, so the connected component decomposition, the meat algorithm is actually very simple. You only combine subheaps that don't have variables in common, and that's a very simple criteria. Yeah, but in the more general case, it's a bit more complicated, but I'm not going to talk about it. So I took this idea of heap decomposition, and I want to try and see whether I can verify fine-grained concurrent programs and prove linearizability. And one of the goals was to create a thread-modular-like analysis. So what's a thread-modular analysis? So there are different kinds of notions. For example, so there are different works. There's one by Flanagan and Kadir, where the idea is that you have different threads. So these are the hexagons represent different threads, and the resources are represented by these small squares. And there, the idea is that you actually create a Cartesian abstraction that maintains the correlation between the local variables of the local state of each of these threads, but it loses the correlations and you also track properties of the global state, but you lose the correlations between the different local states of the threads and the local state of each thread and the global state. But the problem is, this approach works well for programs that have, for example, numerical variables, it doesn't work so well for the heap, because the heap you can think about it as just one single global variable. So it tends to be very complicated, so it doesn't actually buy you too much. So now there's another work by Alexei Gotzman, and what it does is actually he actually lets you split the heap into a set of disjoint components, and he lets you associate a local resource invariant with each one of these separated subheaps. So this is a slightly better approach, but so the problem with this approach is that it only works for coarse-grained concurrent programs. So I mean, if you have different kind of threads, like in the program that I showed you, that can actually access the same kind of object, then you're in trouble. It doesn't actually work. And using the idea of heap decomposition, I have actually a more general approach. And this approach, you can actually have non-disjoint resource invariants. So, for example, you can have a resource invariant for these 4 objects and for these 4 objects, and they may actually overlap. And this is what lets me handle fine-grained concurrent programs. So let me start with the toy example. So in this example, I have a global variable g, and I have local variables x and y. And now what does this program do? It assigns a new object to x. It assigns x to y. And now I want to assert a thread local invariant that always when I get here, x is equal to y. Then I assign x to g. And then I want to verify this assertion, which is actually not thread local. It talks about the global variable that says that g is not null. So this is a fine-grained concurrent program. And so let's just, for example, okay, so for right now, let's just run it with one thread. So let's see how it works. So I start with this memory configuration, where I have a single thread represented by this hexagon. And then I assign x in the object. I assign y to x. And then I assign g to x. So I have just these. So I'll have these 4 possible memory configurations. And in logical form, they're represented by this invariant. You can see that this is a disjunctive invariant. And here I maintain the correlation between the program counter and the equalities and disequalities between all the variables and null. So this is precise enough. But now the question is, how do I actually verify these assertions for an unbounded number of threads? So to do that, I need to consider abstractions for programs that don't have any assumption on the number of threads. So this is an example of one concrete state. It's just one state, but it has numerous threads. So for example, it has 2 threads in program counter 1, 2 threads executing at program counter 2, 3, and 3 threads at program counter 4. So what kind of abstractions can I perform here? So there's a known idea of, it goes back to counter abstraction, and what this idea says is that you actually conflate all the information for all the threads that are at the same program location. So there can only be a finite number of program locations, so you summarize together all the threads at the same program location. And what you get is this bounded heap. And now you can see that we have these summary thread nodes that says that this node represents 1 or more threads executing at this program location. And I have these summary objects that represent 1 or more objects in the heap. And then you can see that I also have these dashed edges that are actually may edges. And after you perform this abstraction, what you see is that you can't even verify a thread local invariant. Right? So because we don't know that x and y, for every thread here, that x and y are actually aliased. We lost this information, which is important. So we lost the correlation between the local variables, and we cannot prove that x is equal to y. So what I'm going to use is the more general kind. I'm going to move to a richer class of abstractions for concurrent programs that are going to use universal quantification. So here I have this thread index that I'm going to add to the predicates. So I'm adding it to the program counter and both to the thread local variables. And this is the invariant this is actually part of the invariant that I get for this program. And so it is index predicates. And each of these disjuncts represent the abstraction of the state from the point of view of just one thread. And I'm going to combine this idea of, so remember that in the beginning I told you that these CNF invariants, they have this infinitary version, which is just universal quantification. So I'm going to combine this idea with heap decomposition. So I'm going to use these more general kind of heap decompositions that allow me to move so before I had this finite number of components that I could define, and using universal quantification, I can have actually an unbounded decomposition of the heap. So, and the information that I lose here is the number of threads, which actually I want to lose. It's not important. It's usually not important. And this idea, I actually adapted this idea to canonical heap abstraction. So here's the example of what happens. So I have this concrete state, and suppose I focus on this one thread. So what I do is I decompose the heap from the perspective of this one thread, and I get an abstract state that looks like this, which corresponds to this disjunct. And here you can see that I actually maintain the correlations between the local variables and the global variables. What this subheap actually represents all the heaps. So now you remember we have this more general kind of decomposition where we can have actually overlaps. But it represents all the heaps that contain this subheap, and also some other number of threads and objects. And we might even have links going from local variables for other threads to this object. But the important information that we have here are the equalities and disequalities between the local variables and the global variables, which is important for this program. What we lost is the number of threads and the correlations between the variables of different threads. So here I'm using the more general kind of decomposition, which is indexed by this thread T. So this is a bit technical, but if you don't get it, don't worry. So I have this binary predicates that are indexed by this T, and what they say is that suppose you choose some object, and then your decomposition predicate captures a subheap relative to this particular thread, and then there's another subheap from the perspective of this thread, and then we decompose. Again, we decompose. But what we get finally, the invariant is actually universal quantification of the disjunction of all these subheaps that we can get. So, okay, so this was a toy example. And now I'm going to come back to this example that I showed you in the beginning, and this concurrent stack implementation, for which I want to prove that this concurrent data structure is linearizable. So let me more or less define linearizability. So linearizability is a major criterion for concurrent data structures, and it provides the illusion that each operation is atomic. And it uses the concept of linearization points. So the push and pop, for example, we can have two threads that are executing push and pop operations, and these operations might take a very long time, and they actually may overlap. But we want to think about them as happening atomically. So linearizability says that for every concurrent execution, there is a corresponding sequential execution where the order between the operations is maintained. So, for example, we can think about this operation is happening taking 0 time at this point of time, and so this is the linearized execution. Okay, and here actually building on top of another analysis that proves linearizability for a bounded number of threads, and the idea is to track a bounded number of differences between the concurrent execution and the linearized execution. And but of course, because the bound that it's tracking the difference that it's tracking is bounded, it means that it can only apply to a bounded number of threads. So this is an assumption that I want to lift, and the linearization points in the kind of algorithms that I'm considering are actually happening at successful CAS operations, and also at successful occurrences of acquiring lock and releasing a lock. And so this analysis uses a special correlated predicate to track partial isomorphism between the concurrent and sequential execution, which must be bounded. And because it tracks the correlation for all the threads, it's feasible only up to 2, 3, or 4 threads, depending on the program. So in the new analysis that I defined, I'm using heap decomposition. And here actually, so what this analysis lets me do, it lets me track bound differences between the concurrent and sequential execution, but the bound is only per thread. So this is what actually lets me handle an unbound number of threads. I'm using the same linearization points, and the kind of correlations that I want to maintain are the ones that are enough to ensure that I actually can that I can successfully detect successful class operations and to find, to actually be able to determine the linearization points, which is important for linearizability, of course. And I'm going to lose the correlations between different threads. And this is what is going to get me analysis that has thread-modular characteristics. So here's an example of a concurrent state. You can see there are 4 threads executing, and some of the objects are actually correlated, and some of the objects, these 2 objects, are actually the result of local mutations that the threads are actually doing, and they mean that there's actually a difference between the concurrent sequential execution. And the kind of decomposition that I want to define here is the one that maintains for every thread the objects that are pointed to by the local variables and the objects that are pointed to by the global variables. And intuitively, this is because for this example program, I want to be able to determine that when I have this cast operation, I actually want to know where the global variable and the local variable are pointing to and be able to update the local variable. And I also have another component which helps me get scalability, which is the correlated component. It keeps the correlated objects and the objects pointed to by the global variables. So if I apply this decomposition, I get the following. So for this thread, I get this subheap. You can see that I'm tracking the correlation between x and t and top. And this is the subheap for this object, for this thread. This is the subheap for that thread, and another subheap for the final thread. And I also have the correlated part, which tracks the correlation between the global object and all the correlated objects. And what you can see is that these subheaps actually overlap. And this is actually important. And so if I decompose them, what I get is these 4 subheaps. So the information that I actually maintain are the correlations between the thread local variables of every thread and the thread local and the global variables and the thread's local mutation. So for example, I remember that this object is actually not correlated for this thread. And the information that I lose is the number of threads, which when I want to analyze this program for an unbound number of threads, and also the correlations between the variables of different threads, which actually gets me this thread-modular-like analysis. So let's look at 2 of these subheaps, what they actually represent. Again, this cloud picture. What they represent is all the heaps that have any other number of threads and objects, and there may be some links between them because I'm not assuming any disjointness. So a lot of information, but what I maintained is enough to actually ensure that for this subheap, CAS is going to succeed. So this is going to be a linearization point. And so this object, for example, is going to become a correlated object after the mutation. And for this subheap, CAS is actually going to fail.
Sorry, I missed what the correlated objects are.
Right.
How are they different from the other posts? Are they just reaching over the top?
These objects?
No, so for each thread local heap, you have sort of these some objects that are
Pointed to by the local variables?
Some objects that are not core.
Oh, okay. Oh, okay, sorry. So this doesn't have to do with the decomposition. The correlations that I'm tracking are between the objects pointed to by the local variables, x and t, and the global variables, and this correlated says that for this, so this object is actually, I'm tracking a difference between, what I'm actually tracking is a partial isomorphism between the concurrent execution and sequential execution. So some objects are actually isomorphic, there is an isomorphic relations, but some of the objects are actually temporarily out of this isomorphism. So you can think about 2 graphs that are almost isomorphic up to a bound number of objects per thread. So this actually represents 2 objects that exist in the concurrent and the sequential execution. And there's actually an isomorphism edge that connects them, but this is implicit here. Whereas for this object, it only exists in the concurrent execution. There is no corresponding object in the sequential execution. So these 2 heaps are actually simultaneously out of isomorphism. And after this cast execution, after this cast operation succeeds, then what it's going to do, it's going to make top point to here, and this object is going to become correlated. So this is a successful linearization point. It's going to become part of the list. It's going to become correlated. Does that make sense? Or yeah, there's some. Okay, I can describe the details afterwards. So so I applied this analysis for three kinds of implementations. One is this tribal stack that I've showed you. One is a two-lock queue. So this is the implementation of a queue with two locks, but actually data races, benign data races. And one is a non-block implementation of a queue. And I verified cleanness properties such as absence of null references, memory leaks, and also linearization. And so this is actually the first automatic verification of linearizability for an unbound number of threads. And you can see the running times and number of states. I think they're quite reasonable, actually. And the properties that I'm actually utilizing in this analysis is that the mutations actually occur very close to the access points of the data structure. So these K separations, for example, for the stack occurs near the global variable top. And the number of mutations, as I've told you, per thread is bounded.
You said first verify. What you said that you're verifying, did you give it an invariant to prove, or did you?
No, there's no invariant. So on the analysis that I'm talking about here, there are no annotations except for the. Sorry.
And so, what do you prove of it?
Okay. So linearizability. So the way it works here is that I tell it. So there is actually a small annotation that says. There's actually a guess of the linearization point. I can actually not automatically try different guesses, but in this kind of program, I say, okay, my guess is that the linearization point are the successive K separations. Try to prove it. And then it goes on to explore the absolute state space, and it proves it.
So it doesn't prove any properties of the queue, for example, or memory safety or anything? Just
Yeah, it also proves them. It also proves these properties, that the list always is always an acyclic list. There are no memory leaks, no another references, and all those sequential properties.
So that's part of this
Yeah.
as well?
Right. All these properties.
So linearizability, I think, is the way he defines it. It's with respect
Oh,
to
sorry,
pre and
just a
post.
second. Let me go back. Sorry. One small correction. Actually, okay. So there's actually, it's not entirely correct. So what I prove here, actually, okay. So linearizability is an interesting property, and what it lets you do. One of the properties of linearizability is that once you so what it lets you actually verify different properties separately. So if you want, so first you actually verify the sequential specification, and if you do it, you don't actually have to do it for the concurrent execution. So actually, these times actually represent proving linearizability, but they also prove null references and absence of memory leaks. But I don't check that the list doesn't become acyclic. This I actually check on the sequential specification, and so this is actually quite simple for lists. Okay.
So linearizability is with respect to the sequential specification, right?
Yes,
So
always.
you do have a pre and post for every like member function of the object.
Right. There is a sequential specification. Right. Right.
So to my understanding, you assume that there's no, or the topology of the threads is simple in the sense that there are no relations between threads.
I don't assume it.
No neighbor relationships who synchronizes with which. So if you have a ring topology, multi-ring topology, it would not fall into this class. Is that correct?
Okay, so I don't assume anything about it, about the connections between the threads. But if I bet on the wrong side, on the wrong kind of decomposition, then what would happen is that I'm going to lose precision and not going to actually be able to prove the property. But I never lose soundness. So if you have this ring topology, then you'd better come up with a different kind of decomposition. And okay, so let me come up with the conclusion. So what I'm promoting is this idea of heap decomposition that helps you scale complicated shape analysis. It's parametric. It lets you uniformly reduce exponential factors, both due to the control, the threads and the objects, and you can use it to create analysis that have thread-modular characteristics, even for fine-grained concurrent programs with no bound on the number of threads. And in my thesis, I have several other results. So I have another kind of, different kind of partially disjunctive abstraction that I haven't described here, which uses partial isomorphism join, and I integrated it into TVL8, became the choice abstraction, and it also gives you very significant speed up. And actually, I'm combining these two ideas that actually combine very nicely. Partial disjunctive abstraction, this partial isomorphism and decomposition. I'm actually using them together. There's this precise abstraction for a single linked list that I showed you earlier. I've shown how to actually compare, shown how to code it in predicate abstraction, canonical abstraction, and compare the two. And so this kind of abstraction actually has been employed by other researchers, and it also has been, and the idea also has been extended to trees. And coming back to this picture, so partial isomorphism join is actually orthogonal, but we can combine them together. They work very well together. And there are some other results that are not in my thesis. So in my first internship with Manav Vidas, I worked on postmortem symbolic evaluation. And the idea there was to take crash dumps and try to produce error traces that would help the developer actually debug the program, find the reason for the bug. I also worked on the MIT algorithm for three-value structures, which we can use to intersect different kinds of abstract states. And this is actually what I'm using to define these decompositions between heaps that might actually overlap. And I also have a theoretical framework for counterexample guided refinement. And okay, so there are still open problems that I want to handle. So I told you about this idea. So this whole idea of heap decomposition that's parametric, it's very nice because it lets you have, you can think about a lattice of different abstractions. So for every point in this space of abstraction, you can have a sound analysis. But now the question is, we have all these multitude of abstractions, which kind do we actually want to choose? I mean, given the program and the property, how do you actually tune them? So this is something that I haven't addressed. I mean, I've done it for a class of programs and properties, but I haven't done it automatically. So I'd like to investigate this. I would also like to try and think about combining decomposition and summarization for interprocedural analysis for concurrent programs. And I would also like to try to prove linearizability for more complex data structures, more complex kind of linearization criteria. For example, ones that depend on the history of the execution. And another thing that I would like to do is define kind of local shape analysis. And the motivation here is that would ultimately let me, hopefully let me come up with completely automatic transformers for these decompositions by inferring the footprints, the part that is actually accessed by a transformer. So actually I haven't described how I specified the transformers, but you have to guess which kind of subheaps do you have to compose. You have to guess it, and then the analysis uses it. It's always sound, but the question is, how do you come up with these specifications? So I'd like to automate this. And here are some questions that you may ask me. Thank you.